So today we're going to be talking about global and local extrema when dealing with functions. So say we have some function that looks like this. So we have a closed dot, which means that point is included in our function. And here we have an open dot. This one's not included in our function. So how we want to characterize these different points. So we notice here we have one of these little swoopy things where it comes down at the bottom and comes back up. And we notice that at this point, the tangent line is horizontal, right? So we call points like this local extrema, and they occur at points where the derivative is equal to 0 at these points here, because a flat line has 0 slope, so the slope is 0 at this point. But we also notice that this point here is much lower than this point here. So we want another way to talk about that. So on an interval like this, we would say that this, if we included this point would then be the global minimum. And here, well, I kind of didn't draw very well, but we can see that this one's slightly higher than this, so this one would be our global maximum, because it's the highest point on the entire interval. So we just needed a way to differentiate between the absolute greatest and just one of these little, dents. So we call these things critical points. So, like I said before, we can find critical points at places like where the derivative is 0, but we also want to check where the derivative does not exist. So an example like this would be if we had a function that came like this, and it hit in a point. At this point, there's no derivative. We can't say anything about where the slope of that line is, right? It could be here, it could be here, it could be here. They would all work. We wouldn't be able to say. So at that point, it doesn't exist, but it could still be a local minimum or maximum. So another interesting thing that we want to look at before we look at these points is we want to look at intervals of increasing and decreasing. So we notice as here the function starts up high and then we start going lower and lower and lower before hitting this point and then coming back up. So let's take a look at this tangent line. Well, this tangent line is sloping down. So if we were to think about this in terms of y equals mx plus b, this would be negative. So that means that a function is decreasing whenever the derivative is less than 0. So recall that the derivative is just at a point, so at a point, say x, or at a point a or b, it doesn't really matter. The derivative at a point is the slope of the tangent at that point. We can also consider it on this side. So notice that at this side, the function is going from down here and it's going up as our x's increase, so we call that increasing. And notice here it's going up, and we notice the same trend, except the m is going to be positive this time. So we say it's increasing when the derivative is greater than 0. And notice that a function has a derivative. So say a function has f of x is equal to x squared. Okay? Well, if we take the derivative of that, we have 2x. Well, 2x is going to be negative when x is less than 0, and it's going to be positive when x is greater than 0. So we have to take into account that this is going to change at different points. At the critical points, in fact, is where this actually changes. So if we have a function, let's take this function. F of x is equal to x squared plus 3x plus 2. So let's break this down and let's factor this. So say we have this is the derivative of function. So say this is our derivative. we want to break this down because we want to find the critical points, okay? So we break this down and we say x plus 2 times x plus 1 is the factored form of this function, where this function is the derivative, okay? So this gives us critical points. X equals -1 and -2, okay? So then we plug these things in to what I call a sign shard. And we take values in between these things. So it's basically like a number line where this is the -1 and this is -2 and this is -1. So here we have x values that go between -2 and -1. Here we have x values that go between -1 and positive infinity. And here we have -infinity and up to -2. So say I can take any number in here. I can take -18, I can take -4. I'm going to take -3 and I'm going to plug it in here, okay? So if I have -3, it's going to give me +9 minus 9 plus 2. So that's going to give me a positive number here, okay? So I don't care what the actual value is, I just care that it's a positive number. In here, well, let's take -1/2, okay? So then you want to go off to the side and you can use a calculator, you can use, whatever you want, but you're going to find out that this is going to be a negative value. And then in here we pick something else. I'm going to pick 0 for simplicity, so 0, 0, and then +2, so this is going to be a positive number again. So we know that the intervals of increasing and decreasing here is going to be, so the interval of increasing is going to be x is in -infinity up to, and here we include 2. So we want to make sure that we include the critical point. Now some textbooks, I have seen discrepancies, but for us today we're going to include the point, because if it's 0, it's technically like it was increasing up to 2 because it, got to the max point that would be coming all the way, increasing up and including this point. And then we're just going to do union -1 and positive infinity, right, from this here. And then we have the interval of decreasing, and we get this interval here. So it's x is in, and we're going to include it again. We include the critical point because at 0 it's neither increasing nor decreasing, but so it's kind of doing both at the same time. Again, there's discrepancies here, so if you've learned it the other way, then that's fine as well. And it's just going to be from -2 to 1. And those are our intervals of increasing and decreasing. So notice that if we take this, so it's going from increasing to decreasing to increasing again. So we have increasing to decreasing to increasing again. At this point is -2 and this point is -1. We notice that we're going to have this local maximum here. And we notice that we're going to have a local minimum here. Okay, so this is another way where we can really tell what's happening. The other thing to do is then to draw it. So we know that as it's increasing, it's going to do that, and we know that here the derivative is equal to 0. Because if we plug in 0 into the, right, if we plug in -2 into this derivative, it's going to give us the derivative of 0. So at this point we have f prime of x is equal to 0. Same, and here as well. So we know that those have to be the local minimum and maximum. So once we have that and we have these critical points, we also want to check the endpoints. So most people don't include endpoints in their critical points, but I like to, because it reminds us that we want to check them whenever we're dealing with a function like this. So here we could have this function and it could have continued off to infinity on both sides, but no, we decided to stop it on both sides. So when we want to find the global extremum, we have to check endpoints. So these critical points are going to give us all these numbers. They're going to give us x1, they're going to have x2, x3, however, and each of these are critical points. So maybe one came from D and E, one came from the derivative being 0 and 1, and 2 of them came from the endpoints of the integral. So what we want to do is we want to take our original function and we want to plug it in. So we're going to do f of x1, f of x2, dot, dot, dot. And we're just going to keep doing however many critical points that we have. So it doesn't really, but we want to make sure that we're using the original function. We're not using the derivative here. So once we figure that out, we'll get, various different y values. You'll get y1 equals y2. And then whichever one is the biggest y value, that's going to be our global maximum. And the smallest value will give us our global minimum. So that's all I have to say about global and local extrema, so minimum and maximum. Next time we're going to be covering things to do with concavity. So that's basically determining if it's kind of swooping up like this. This is concave up and this one's concave down. We'll talk about that next time. If you want some questions and examples, they're down below. Hope this helps. If you have any comments or suggestions for the next video, let me know. Thanks so much. Bye.